back to Chem 140. This is the last lecture before the exam, and we're actually doing pretty good on time here. So we're going to finish Unit 8 today. I'm going to start a little bit of Unit 9 just so that we use, like, the first hour. I actually don't expect that we're going to go much past the hour, so what I will do is we'll take the 10-minute break. And if anybody has any questions, you can type it in the chat. And then after that, we'll dismiss. We won't use the whole period tonight. Because I know a lot of people are starting to get down to the wire, and there's lots of shit to do. And you'd rather be doing that than watching me talk about ionic compounds, probably. Speaking of which, last call for quiz number 3 is tonight. Make sure you get that in. It will close at midnight. And then I need to toggle on the answers so that you can actually see them. Lab number 2 is also due today. You have until tomorrow to turn it in, but again, try and stay on top of this stuff because more stuff is coming. That stuff being the exam on Friday. Okay? All right, so we left off here. We were just going to very briefly talk about some trends on the periodic table that are going to be helpful for us in the future. Okay? So the first trend that we're going to concern ourselves with is metallic character. This is going to become immediately relevant in Chapter 9, or Unit 9, I guess we should say. If you take any period on the periodic table and you just go left, what you observe is that the substances you see become more and more metallic. So this is really evident if you look at period 3. Period 3 is a great example because chlorine on the very far right is a gas. You move over 2 spaces and you immediately just hit phosphorus, which is a solid. Sulfur is also a solid. I just had the picture for phosphorus handy. And then go over a few more spaces, and then you get to aluminum, which is the shiny metal that we would expect. So things immediately become solids, and then they become metallic looking, and then they become metallic acting. So silicon looks kind of metallic. It's shiny, but it doesn't really look silvery like we would expect. But aluminum definitely is. Magnesium definitely is, and sodium definitely is. Now you can do this going up and down too. I'm going to use group 15 actually for this because nitrogen is a gas at the very top. You go down immediately, you get to a solid, already a little bit more metallic. Then we go down to arsenic. It's already got the right color. It just doesn't have the right consistency or texture. It's a metalloid. If we go down to antimony, though, antimony looks very metallic. And then we get down to bismuth, which, I mean, this looks what a metal would look like if it crystallized. Although bismuth itself is kind of a weird sort of crystalline metal. But bismuth has all the properties of a metal. It conducts electricity and heat. It is malleable if you hit it, although why would you want to? Because it looks really pretty as it is. But you can easily hammer it down into a sheet or do whatever it is you need to do that. So metallic character, things become more metallic as you go left and down on the periodic table. Note that these are how matter behaves statements and not why matter does this. We're not super concerned with the why at this point in the class. We're going to talk about that more in quantum mechanics in 161. All you need to know is just how the trend works for these trends. This other trend that we have here is atomic size. This is not going to be super relevant in this class, but it'll be very relevant in 161. And it's covered in the text, so we might as well just talk about it a little bit here. On the screen, you'll see a bunch of numbers. These numbers are atomic radii in picometers. And you can see that as you go down the periodic table, this being group 1A or group 1, atoms get bigger. They don't get bigger in a linear fashion, though. They get bigger quickly at first, and then it slows down, but still increases. So kind of like if I drew a graph like this. This is what the size is doing. So this would be down periodic table, and this would be size on our graph here. It doesn't really level off, although we don't have very many elements past cesium down there. So francium is a little bit bigger than cesium. And then whatever comes after francium, whenever it's discovered, whatever element 119 is, would be bigger still. Now, the reason for this is because when you stick electrons around the atom, they have to get increasingly farther and farther and farther away. And that's because electrons take up space. They push each other away. And as you cram more electrons around a nucleus, there's only so many places they can go that aren't just further away. And so eventually your electrons have to be further away. And that's what's happening here is the extra electron that we're tacking on is going into what we'd call a new layer. In quantum mechanics, we'll call those shells. Now, if adding more electrons makes things bigger, it would make sense that going left to right would make things bigger too. But it turns out that that's actually the opposite effect of what happens. And there's a specific reason for this that we're going to cover in quantum mechanics. But the gist of it is that as you go from left to right, not only are you adding electrons, but you're also adding protons. And you're adding them in such a way that the electrons are roughly the same distance from the nucleus, but the protons you are adding pull harder than the extra electrons added repel each other. And so the result is that the protons end up winning this sort of tug of war, and the atoms get smaller as you go left to right. Again, this isn't linear. It tends to decrease fairly slowly at first, and then it starts to speed up. And then when you go to the next row, everything gets bigger again because the extra electrons you're adding on go on to the next layer. So size does this very strange thing when you just look at it linear. It goes down and then it jumps up and then it goes down and jumps up if you're looking at the entire periodic table. That's a little too complex, so really all we need to care about is that for size increases as you go down and to the left. And that's all you need to know. You do not need to know the reasons why that happens for the exam. It's just going to ask you, sort these by size. And you just put them in order from biggest to smallest or whatever it asks you to do. Make sure you are actually following the order it tells you. If something tells you smallest to biggest and you do it backwards, Canvas will mark it wrong, obviously. So be careful. All right. So in each of these pairs, what I want you to do is I want you to select the member of each pair that is both more metallic and which is larger. And you're going to notice that they're the same trend, right? As things get bigger, they also become more metallic. So select the member of each pair of atoms that is more metallic and is larger. Okay? We'll go over the answers in about 3 minutes or so. One more minute, we'll go over the answers. All right. So we're going to look at the periodic table, and we're going to pick basically the element that is further to the left or further down, because that's going to be the more metallic of the pair. So of these two, chlorine and sulfur, which one is further to the left or which is further down? Well, they're in the same period, so they're the same elevation, we'll say. But sulfur is further to the left. So it's going to be more metallic and the larger of the two atoms. How about gallium and indium? Well, they're the same left-right coordinate. They're in the same group, which is 13, actually. But indium is further down, so it's going to be the larger of the two atoms. We can do the same thing with magnesium and aluminum. There is a giant gap between the two of these, but for our purposes, that gap doesn't really exist as far as the atoms are concerned, because the atoms just count one proton after the other, going left to right. So since magnesium is further to the left, it's going to be bigger than aluminum. Same thing for potassium and calcium. Potassium is further to the left. And then finally, barium and radium. Radium is further down. And so it must be bigger. Now, you can end up in some weird situations like this that may make it harder to predict if you're not careful. So for example, if I did this, so here's two elements on the periodic table, calcium and rubidium. Well, obviously, calcium is the smaller of the two, because rubidium is further to the left and further down. So that's an easy answer. But what if I ended up going the other direction? What if I did something like this and I picked, like, say, aluminum and germanium? Then you have one that's further to the left, but you have a different one that's further down. What's the answer here? And the answer is it's impossible to determine. So if you end up in a situation where one of the two choices is further left, but the other one is further down, you cannot discern the answer without actually doing the experiment. Because we're not really following the trend here. We're sort of, one is following it, but the other is too. Which one wins? It's hard to say. There are some justifications you can use in quantum mechanics to figure that out, which is bigger, but we're not going to worry about that until we talk about electron configurations in 161, so don't worry about it now. Okay? So if you see a question like this where you have them diagonally offset and one is further left but the other is further down, The answer is cannot be determined. I don't think that you will see that on the Canvas quiz because I don't know what option I would have you type in for that, or check a box or something like that. So you probably won't see that. All right. I think that that's the end of Unit 8. Yeah, it is. So let me get your happy orc here. Sound effect. All right. I am going to load the slides for Unit 9, so we're going to do just a little bit of Unit 9. Because we have, like, it's only been 20 minutes for class here, so let me exit out of this one. And we'll boot up Unit 9 here. We'll talk a little bit about ionic compounds. Just a little bit. We're going to do Lewis structures tonight, which is the easiest thing that you'll do in this class, so it feels appropriate to use our time to do that. And this will just get a little bit of our content out of the way so that we aren't going to cram so much at the end. All right. I didn't mean to click on that, sorry. Unit 9 deals with ionic... Oh, what I should first preface this is, remember that your exam is Units 1 through 8. So this will not be on Exam 1. This is Exam 2 that we're starting on. So if you're like, nope, I don't want to deal with this tonight, go ahead and check out right now. That's totally fine. You can come back and watch this video at any time because it'll be posted to YouTube. I just want to use the time effectively so that we don't have a 20-minute lecture and then that's it. I'll use the rest of the hour. We'll take our break, see if there's any questions, and then we'll call it a night. But towards the end of the quarter, we are going to start to run into time issues because there's a lot of content and a lot of math at the end of 140. So we start to slow down a little bit once we hit like Unit 13, where the math comes back. But for now, we'll try and use that time to the best of our ability. So Unit 9 talks about ions and ionic bonding. How do we make ions? What are the structure of these compounds? What charges occur on atoms commonly, and so on and so forth. All right, so we're going to start talking about bonding. A bond is some sort of force that holds two atoms together. Now, there are all sorts of different types of bonds that we will encounter. We're only going to really talk about two of them in this class. The first one's the ionic bond, which is what we're going to talk about in this class, or in this unit. And then in Unit 10, we're going to talk about covalent bonds in a little bit more detail. Now, all bonds use electrons. Which electrons are used is going to be important, and we're going to discuss that here. How the electrons are used determines what type of bond we form. So an ionic bond will involve transferring electrons from one atom to another. We just give the electron away. This changes the number of electrons and protons we have and creates a charge, and then those charges attract to each other. A covalent bond, on the other hand, involves something different. Electrons are pooled and they're shared equally, more or less, and we create molecules with bonds between specific atoms that form different structures entirely. Our focus is going to be on ionic bonds. We'll just highlight the important terms here that you'll need to know for Unit 9. So yeah, let's talk a little bit more about ionic bonds here. So on the screen, I have drawn a model of various atoms. Now, remember that when we talked about electron clouds, that electrons do not live on constrained rings, and that this is an exaggerated model. These layers of electrons are the electrons are roughly in this distance from the nucleus, and then the electrons past that are much further away. Because again, remember, the nucleus of the atom is very, 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 very tiny compared to the electron cloud. What we care about here in this diagram, though, is that there are two sorts of classifications that we can give electrons. So we can give electrons the outside classification if they live on the outside of the atom, the outermost area. So I don't really need to highlight all of these, I guess, but now I'm sort of committed to it. So these electrons I've highlighted are the outermost electrons. We're going to give those a special term, valence electrons. A valence electron is the electron that is on the outside of the atom. In other words, if this is my atom and this is another atom and these two bonk into each other, the electrons that interact with each other are valence electrons. Now that's important because all of our bonding is going to involve electrons interacting with each other, and therefore only the electrons on the outside participate in bonding, because those are the first ones that see each other. So valence electrons are the outermost layer, and there's going to be some number of electrons on the outermost layer. Any electrons that are inside, oops, I thought there was something that said that. Any electrons that are on the inside, so I'll color these in a different color here. So we'll color them just kind of pink, I guess. So any electrons on the inside here, I'm filling in kind of sloppily, but that's okay. So the pink electrons, these are called core electrons. And they just hang out. Those electrons don't do anything in particular of importance for bonding. They're still useful in various ways, and we can detect them. And we'll talk about that in 161 as well. But for our purposes, we're going to ignore the core electrons. We only care about valence electrons. How many valence electrons does an atom have? You can determine that by looking at the group number. How many layers of electrons are there? You can determine that by looking at the period number. Okay, so, oops, I got to get the correct color here. So, the number of layers of electrons is equal to the period number. So, for instance, chlorine is in period 3, so you can see that there are 3 layers of electrons. Iodine has 5 layers of electrons because it's in period 5. Hydrogen would have 1 layer of electrons because it's in period 1, and so on and so forth. As the layers increase, you can put more and more electrons in there, and that's why the rows get bigger and bigger and bigger as you go down the periodic table. So period 1 only has 2 elements in it, but period 2 has 8 in it, and period 4 has 18, and so on and so forth. Now, the number of valence electrons that you have is equal to the group number if you are looking at group A elements. Now, the easier way to do this, if you're not using a periodic table that has group A elements on it, is we're going to do the following. So, the number of valence electrons is equal to the ones digit of the group number. So, because all of these elements I've selected are in group 17, the ones digit of that is 7, and therefore these have 7 valence electrons. So what this becomes now is just a find the element on the periodic table, see what group it's in, and then read the ones digit. That's how many valence electrons there are. Now, the strength of this strategy is that I don't have to have you worry about A and B anymore, and then I'll just never give you B elements anyway, because transition metals don't really follow this pattern, but transition metals don't really follow much of any pattern, really. We'll learn in 161. So we're going to ignore those and just stick to this, and this pattern will work for the main groups that follow these sorts of behavior, which is groups 1 and 2, and then 13 through 18. You just need the ones digit, and that'll give you the number of valence electrons. So let's do an example. If we find phosphorus on the periodic table, phosphorus is in group 15. The ones digit is a 5, so that would be 5 valence electrons. Oh, I also asked you for the valence shell. And so the valence shell would be, well, it's in period 3. So it would have valence electrons would be in the 3rd shell. We're not going to care terribly much about the valence shell. We're going to care mostly about this one. This is the important one, is the number of valence electrons. And of course, my text appears right over where I wrote it. What happens if you have an ion? What if I change the number of electrons here? Well, let's look at oxygen by itself, first of all. So it's in group 16. So that would be 6 valence electrons. But then if I did this to it, and I gave it a negative charge, I have to add that in here. And so now it would have an additional electron. What valence shell is it in? Well, it's still in period 2, so it would be valence shell 2. Now, the same thing happens if you subtract electrons, but you do get an interesting situation if you subtract all the valence electrons. So, for example, calcium is in group 2, so it should have 2 valence electrons. But if I make it plus 2, I reduce this by 2, and thus I have 0 valence electrons. Now, if I have calcium with rings of electrons going around the outside, like this, and then I remove all of the electrons, that's the same as me going boop and get rid of that ring, right? That layer doesn't exist anymore. If this happens and you remove all the valence electrons, then what ends up happening is that the previous layer, which is now full of electrons, becomes the valence layer. And so we'll just count back 2 elements and see what we land on. Well, if you are on calcium and you go back 2, you land on argon. So calcium plus 2 should have the same electrons as argon does. So we'll just report whatever argon is, which is... Gotta remove my text here. Oh, excuse me. So if I remove the electrons from the valence shell of calcium, it now looks like argon. And so we'll just report argon's valence electrons. It's valence shell 3 and has 8 valence electrons. That's kind of a weird sort of edge case that happens with metals if you remove all their valence electrons, but that's going to be really relevant to us later on when we talk about the octet rule, because atoms that ditch all of their valence electrons attain an octet. That'll be useful to us later. All right, so what I want you to do is tell me the valence shell and the number of valence electrons for each of these atoms and each of these ions. So be careful, I have adjusted the number of electrons down at the bottom. And you may end up in a situation where you remove all the valence electrons and then have to go down to the previous layer, okay? Use the periodic table to do that. We'll go over the answers in about 5 minutes or so. Type in anything you'd like in the chat, just to compare your answers with other people. All right, one more minute and we'll go over the answers together. All right, let's go over the results here. So have a periodic table in front of you for this because you're going to need it. So arsenic here, I'm going to make a little table here. So we're going to say period group. All right, so arsenic is in period 4. So its valence shell will be 4. And it's in group 15. So the number of valence electrons will be 5. Because we're going to use the ones digit. Boron is in period 2, so it's valence shell 2. It is in group 13, so it has 3 valence electrons. Carbon is in period 2, so it's also valence shell 2. It's in group 14, so it has 4 valence electrons. For these next few elements, what we're going to do is I'm going to write down the default form without the ion, and then we'll adjust it for the ion. So for fluorine, it's in period 2, so it's still valence shell 2. It's in group 17, so it should have 7 valence electrons. But then this minus right here adds an additional electron to it. For barium with a 3 minus charge, barium is in period 3, 4, 5, 6, so it will have valence shell 6. It's in group 2, so it should have 2 valence electrons. But then we're going to make it 3 minus, which means we're going to add 3 extra electrons to it. I'm going to skip over potassium for now real quick. We'll do xenon just so it's in period 5. So it's valence shell 5. It's in group 18, so it has 8 valence electrons. Now, potassium plus, let's just look at regular old potassium. So period 4, valence shell 4. The group number is 1, so it should have 1 valence electron. I'm going to change my ink color here. I'm going to remove an electron, so this is going to be 0 valence electrons. But when you have 0 valence electrons, you just go back down to the previous shell. So this becomes 3, and then this becomes 8. Because now it looks like whatever the element is before potassium, which is argon. Okay, you do have to do a little bit of a weird song and dance for ions that you strip away all of the electrons from the valence shell for. All right, let me know if there are any questions. That's how you count valence electrons. We're just going to look at the group number, use the ones digit, and then we're going to adjust that very slightly based on whatever the charge is on the ion if we're looking at an ion. All right. It's already It's already 5:45, so I'm going to put the break timer up. I'm going to just let any questions that you might have about anything you want get populated in the chat. If you have a question for me, I'll answer it after the break is over. If I don't get any questions, then we'll just call it a night here. So you'll have an extra hour to finish up your quiz, work on the lab report, or do whatever it is that you want to. So I'm going to put the timer up again. I'll start the clock. We'll go back to get the Zelda wave going here. And I'll see you in about 10 minutes. Make sure to drop any questions you might have in the chat. we're back. So I have one question in the chat from a quiz question. So let me go to this. We don't actually need the PowerPoint up anymore. So let me... Where is it? There it is. Boop. Okay. So you can see the question in the chat there. So a dog eats... I can't read the question because I'm trying to read it from the chat or from the stream window. So let's see here. So dog eats 230... Oops. I can't write numbers apparently. Let's do that in black too. 233.9 grams of food per day. And the question is, how many years to eat 147.5 pounds of food? Of foods. There we go. Okay, so we're going to start with that number, but we're going to do pounds of food because that's the number we're starting with. We can turn that into grams of food because we can look up the conversion from pounds to grams. And if you know the number of grams of food he eats total, then you know the number of days that will take using this relationship right here. And once you know that, you then can convert to years. So let's do that. So first I'm going to write in all the relationships. So 1 pound is 453.6 grams according to Google. I looked that up during the break, just so we wouldn't waste time on that. And then the number of grams of food per number of days, that's this relationship right here. So 233.9 grams is 1 day. That's a day's worth of food for the pup. And then 1 year is 365.25 days. I believe that number should be, this number right here should be given to you in the problem statement, just because I know sometimes people will use just 365 because that's what you know, but we don't know how many years this will take, and if any of those years in there are leap years, so let's just account for that. All right, so, oops, not grams, sorry. This is the amount of food that my dog will eat. I'm going to turn pounds of food into grams of food. You don't really need to write the word food here, but I'm just going to do it to be complete. And then we'll turn grams of food into days. And then we'll turn days into years. So the problem is asking us how many years. So if we do this dimensional analysis, this should give us the answer in years. And now we'll just run the numbers. So 1 pound is 453.6 grams. In 1 day, the dog consumes 233.9 grams. That's probably not a puppy if it's eating that much. And there is, in 1 year, 365.25 days. So we'll punch it all in the calculator, see what we get. And the answer that I got was 0.783 years. I need another sig fig, don't I? 0.7831 years. There we go. Now, if we look at sig figs here, so this number has 4 sig figs. This one has 4 also. This has 4. This has 5. So my answer should have 4. Oops, there we go. All these 1s are exact. Now, if the problem tells you only report it to X number of sig figs, you would then truncate your answer down. So most of my problems say report to 3 sig figs. So if this one said 3, you just put 783 in there. You could drop this 1. All right. So that should be the answer. Was that the answer that the quiz stated for you? I mean, I can also look that up. Yeah, I'm in quiz 2 right now. Let me see if I can find your quiz here. Yeah, it looks like report to 3 sig figs, and this is that the answer should be the number that's on the screen there. Yeah, okay. Okay. I do know that on some occasions, there are, like, so I had to program all these formulas in. So the formulas are pretty reliable because I test them. Like, I actually go through and I do the first 2 of, like, the 100 that I generate. And if those 2 work, then odds are all the remaining ones work. You do sometimes hit edge cases where if you, like, land very, very, very close to a number, it will give you a weird result. And if that happens, let me know. Like, if it's expecting 0.783 and you typed in 0.792 or something like that, I can look into that. Okay. Oh, okay. Yeah, you had the wrong conversion for grams and pounds. Okay, cool. So that's an easy mistake to make, so just be careful. But yeah, otherwise it looks like that's how you do it. It doesn't look like there's any other questions, so I'm not going to hold people here to wait for questions. Instead, what I'll encourage you to do is bring them to the Q&A tomorrow. Tomorrow is only Q&A, so we're just going to hang out. If nobody has any questions at the start, then what I'm going to do is I'm going to start by just asking you a question, which is, what do you think will be on the exam? We're going to create a sort of study guide. And we'll just go through all the chapters one at a time. And we'll be like, what topics in this chapter could you be tested on? And we'll type them out. And then it'll be on the screen and I'll just share that document with everybody and you can access it. Okay? So that's the agenda for tomorrow, but that's it for tonight. Let me know if you have any other questions over email or Discord. Make sure to use the class Discord. It's getting a lot of use for several of my other classes. I think this class is doing pretty good at using it too. And it's there for your benefit. So, yeah, that's really all I have. Have a good night. Make sure to get quiz number 3 in. It closes tonight. Lab number 2 is due today. Get it in by tomorrow. See you for the review.